Hello, this is Ellie, and today we're going to learn about acids and bases. Acids and bases are one of the most important topics in chemistry. They show up pretty much everywhere, from titrations to equilibrium and buffers and basically a lot of things. So it makes sense to learn about them so we can confidently use them in chemistry. Today we're just going to hit the tip of the iceberg. We're going to go through the basics. What are acids and bases? And what they have to do with pH. So let's get started. First, some terms to know. The Arrhenius theory is one of two theories we'll be exploring today, and this states that substances either add H+ or OH- when dissolved in a solution. And I'll elaborate on this more in future slides. The other theory is the Brønsted-Lowry theory, and this states that substances either give or receive protons when dissolved in a solution. So we'll be comparing these two theories and using them to identify acids and bases. A conjugate acid or base is a substance that's usually present on the opposite side of a chemical reaction, and it's related to a base or acid, respectively, by either having an extra proton or a missing proton. And that is essentially an H+ ion, since the hydrogen atom has one proton and one electron. So remove the electron and you just have one proton. pH is a measurement of how much H+ is in a solution. And similarly, pOH is a measurement of how much OH- hydroxide ion is in a solution. And lastly, amphoteric describes a substance that can act both as an acid and a base, depending on the chemical reaction. Alright, let's now talk about the Arrhenius theory. So, this theory states that acids, when they're dissolved in water, release H+ into solution, while bases, when dissolved in water, release OH- into solution. And this theory is quite useful when it comes to identifying acids and bases, except it does have a limitation. This theory is limited to only aqueous solutions, and there are chemical reactions where gases are formed or you're mixing two gases together, and those can also be acidic or basic. So this theory doesn't work in every scenario. But let's see the Arrhenius theory in action. So here we have this pretty common equation. HCl plus H2O goes to H3O+, which is the hydronium ion, plus Cl-, the chloride ion. Now, we don't really see an H+ in the equation, but we can simplify this by taking the water out, since this is an aqueous solution and there essentially is water literally everywhere. So we can simplify this and make it HCl going to H+ plus Cl-. Now, this is a pretty standard dissociation of HCl in water, but we can see that when HCl is dissolved in water, it releases H+, which makes HCl an acid, according to the Arrhenius theory. And if you can't simplify, just know that an H3O+ is pretty much interchangeable with an H+. What about a base? What does an Arrhenius base look like? Well, we can do the same thing with NaOH, sodium hydroxide. So when we put NaOH in water, we get the sodium ion plus the hydroxide ion plus water? Why is water on both sides of the equation? Well, again, we can simplify this and take the water out because this is an aqueous solution. So we essentially get NaOH going to the sodium ion plus the hydroxide ion. And again, this is a pretty simple dissociation. Of course, sodium hydroxide separates into sodium and hydroxide ions. But here we can see that OH minus is released into the solution, and that makes NaOH a base, an Arrhenius base. So we can clearly say that hydrochloric acid, HCl, is an Arrhenius acid, while NaOH, sodium hydroxide, is an Arrhenius base. But again, acid-base reactions aren't just aqueous solutions. Sure, a lot of them are. But what about gaseous reactions? How are you supposed to use the Arrhenius theory to figure out what is an acid and what is a base in that? The Arrhenius theory just doesn't cut it. So to solve this, scientists came up with another theory, the Brønsted-Lowry theory. And this is named after the two scientists who came up with this theory. What the Brønsted-Lowry theory states is that acids are essentially proton donors. They readily give protons away in a chemical reaction, while bases are proton acceptors. They readily take protons in a chemical reaction. And this is a lot more versatile because it doesn't rely on H plus or OH minus being released into a solution. It only relies on H plus being given or accepted. And the fact that it doesn't have to be released into a solution means that you can apply it to a gaseous mixture. Let's look at some examples of Brønsted-Lowry acids and bases. So we have a pretty similar equation here to the Arrhenius ones. HCl plus NaOH goes to NaCl, table salt, plus H2O, water. And here HCl is in its gaseous form, so it's not exactly an aqueous solution. So let's identify the Brønsted-Lowry acid and the Brønsted-Lowry base. Now looking at the Arrhenius side, we figured out that HCl is an Arrhenius acid and NaOH is an Arrhenius base. But just because a substance is an Arrhenius acid or base doesn't mean that it is also a Brønsted-Lowry acid or base. Remember, the Arrhenius theory is limited to aqueous solutions. So a Brønsted-Lowry acid or base may not always also be an Arrhenius acid or base. So it's not super clear which substance is giving the proton and which substance is accepting it. So let's simplify this by writing the net ionic equation. So since HCl is in gas form, we leave it as is, and NaOH goes to Na plus OH minus, and that all goes to Na plus Cl minus plus H2O. And let's get rid of the spectator ions, sodium, and we'll get HCl in gaseous form plus OH minus goes to Cl minus plus H2O. Alright, now this equation is a bit clearer. And we can see that there was an HCl on this side, but that HCl became just Cl minus. Now, where did that H plus go? Well, that H plus went to the OH minus. Remember, H2O is the same thing as HOH. So this hydrogen ion essentially broke off the HCl and went and attached itself to the OH minus to make water, which means that the HCl gave this H plus and the OH minus accepted it. So this means that the HCl is a Brønsted-Lowry acid since it gave away that H plus, while the OH minus is a Brønsted-Lowry base since it accepted that H plus. But what about amphoteric substances? We didn't quite touch on that. Now, if we go back to the equations we saw on the Arrhenius theory slide, let's write them down here. HCl plus H2O goes to H3O plus, which is the hydronium ion, plus chloride ion. Okay, now here we can apply that same Brønsted-Lowry theory, and we can see that the H from the HCl went straight to the water and joined with it to make the hydronium ion. And that left the chloride ion all by itself on this side. So here, the HCl is acting as a Brønsted-Lowry acid, while the H2O is acting as a Brønsted-Lowry base. But what about the NaOH one? The NaOH was determined to be an Arrhenius base. So let's see how that plays out. We have NaOH plus H2O. Let's write this a different way. We're going to put the water first, plus Na plus OH minus. It doesn't really seem very clear where NH plus is being transferred from NaOH. There's no H in NaOH. There is an H in the water. Let's simplify this and make it a net ionic equation. Okay, but that just all cancels out, right? This isn't quite how we would figure out which is an acid and which is a base, but just to demonstrate, I'm going to only cancel out the sodium on either side and leave the hydroxide and the H2O alone. So we essentially have OH minus plus H2O going to H2O plus OH minus. This can be confusing, but it helps to think of the H2O and the OH on this side as completely different molecules from this H2O and this OH. So here, the H2O is actually giving away one of its hydrogen protons over to this OH minus. And when it does that, this OH minus becomes this H2O. And if you give away an H plus from H2O, the H2O becomes OH minus. And that's why this equation ends up like this. These two are essentially completely different molecules from these two. But what does that mean in the context of this chemical reaction? What it means is that H2O is acting as an acid. It's giving away a proton to this OH minus, making NaOH a Brønsted-Lowry base. And again, just because a substance is an Arrhenius acid or an Arrhenius base doesn't mean that it is also a Brønsted-Lowry acid or Brønsted-Lowry base. But wait a second. In this equation, H2O is a base, but in this equation, H2O is an acid? That can't be possible. How can H2O act as both an acid and a base? Well, H2O is an amphoteric substance, and it's the most common one you'll see when you're working with acids and bases, although there are other amphoteric substances. But depending on the chemical reaction, H2O will either accept a proton or give away a proton. It just depends on what it's reacting with. HCl is a pretty strong acid, so it's going to want to give away its hydrogen ion more than the H2O would want to. And NaOH is a much stronger base, so it would want to accept a hydrogen ion much more than an H2O would like to. Alright, now that we've explored these two theories, let's move on to the idea of conjugate acids and bases. If you've encountered chemistry and are a bit familiar with acids and bases, you would have heard of this term. But what are these? It's essentially an acid-base pair. So when you add a proton to the base, you get its conjugate acid. And when you remove a proton from the acid, you get its conjugate base. Given this, let's identify some acids, bases, and their conjugates. So here we have this net ionic equation from the Brønsted-Lowry theory slide. HCl in gaseous form plus OH minus goes to Cl minus plus H2O. And we established in the previous slide that HCl was a Brønsted-Lowry acid and OH minus was a Brønsted-Lowry base. So that's simple enough. But what is the conjugate acid and what is the conjugate base? So looking at this, we add a proton to the base to get its conjugate acid. So if we add a proton, an H plus, to this OH minus, what would we get? We get water. So this is OH minus's conjugate acid. And as for the conjugate base, when we remove a proton from this acid, we get the chloride ion. So the chloride ion is the conjugate base. Simple enough, right? Just identify the acid and the base, and then from there, just remove a proton or add a proton to figure out its conjugate. Another interesting thing about an acid-base pair is that they essentially have inverse strengths. A strong acid will have a conjugate base with negligible basicity. So essentially, the HCl, which is a very strong acid, has the chloride ion as its conjugate base. And the chloride ion is a very weak base because HCl is a strong acid. If you put chloride ions into a solution, it will have essentially no effect on the pH of the solution. Similarly, a strong base will have a conjugate acid with negligible acidity. The hydroxide ion is a very strong base, which means that H2O, its conjugate acid, is super weak. And of course, we know that water is neutral in pH, so that makes sense. Again, a strong acid makes for a very weak conjugate base, and a strong base makes for a very weak conjugate acid. With that in mind, let's move on to pH and pOH. So these quantities are used to determine the acidity of a solution, or the basicity, either way. pH and pOH are logarithmic scales. Why are we using a logarithmic scale for this? It's because H plus and OH minus concentrations are super small. Even the tiniest amount of change can make a huge difference in pH. So just using H plus and OH minus concentrations as a measuring tool makes it super hard to quantify the acidity. And a logarithmic scale like the pH scale makes acidity much easier to measure, since it's essentially a power scale in powers of 10. The pH scale goes from 0 to 14 and it measures the concentration of H+, while the pOH scale similarly goes from 0 to 14 and it measures the OH minus concentration. These equations here allow you to convert the concentration of H plus or OH minus to pH or pOH respectively, and vice versa. Let's try an example of each. So let's say we have a solution and its H plus concentration, the brackets signify concentration, is 2.6 times 10 to the power of -7 molarity. Now to convert the H plus concentration to pH, all we have to do is take the negative log of it. So the negative log of 2.6 times 10 to the -7 is 6.59. And the reason we have 2 decimal places here and 3 significant figures in total is because when you take the log of something, the answer has the same amount of decimal places as there are significant figures in what you're taking the log of. So let's do a pOH calculation now. Let's say another solution has an OH minus concentration of 3.7 times 10 to the -4 molar. So we do the same thing except with the OH minus to find the pOH. And that is negative log of 3.7 times 10 to the -4, which is equal to 3.43. Something else to know about H plus and OH minus is that their concentrations are inversely proportional in a solution, in an aqueous solution, that is. This is because of the dissociation constant of water, which is represented as Kw. The dissociation constant refers to the autoionization of water. Water actually ionizes or dissociates in really small amounts. Its dissociation constant is 1.0 times 10 to the -14. And there are a bunch of things that end up with this equation, that the H plus concentration times the OH minus concentration is equal to Kw. But at 25 degrees Celsius, the H plus and the OH minus concentrations are equal at 1.0 times 10 to the -7. This has been figured out through experimental data. This means that at 25 degrees Celsius, water has a dissociation constant of 1.0 times 10 to the -14, and it also means that in any aqueous solution at 25 degrees Celsius, no matter what is in that solution, the H plus concentration times the OH minus concentration is always going to be 1.0 times 10 to the -14. So either you can have a neutral solution where the concentrations are equal, or you can have an acidic solution where H plus concentration is more than the OH minus concentration, or you can have a basic solution where the OH minus concentration is more than the H plus concentration. And since the pH and the pOH are equal to the negative log of the concentration of H plus and OH minus respectively, what we can do is we can take the negative logs of both sides of this first equation. So we get negative log of H plus times OH minus is equal to negative log of 1.0 times 10 to the -14 and this negative can be distributed to all of it, so this is essentially negative log H plus log of OH minus goes to the negative log of 1.0 times 10 to the minus 14. And what this means is that negative log of H plus minus log of OH minus goes equal to negative log of 1.0 10 to the minus 14. And since these are equal to these, this is essentially pH. So this is pH, and POH is negative log of OH minus, so this is POH plus POH. And the negative log of 1.0 times 10 to the minus 14 is 14. And that's where we get this second equation from. Alright, now we can do more things with these equations. For example, if we have the pH of a solution, we can find its POH. So if the pH of a solution is, let's say, let's go with something simple. If we have it as 7.5, that's our pH. Its POH is simply 14 minus 7.5, which is 6.5. Or we can use the H plus concentration to find the POH. So if we didn't have this pH here, and instead we had a concentration, we could use this equation to find the pH, and then just subtract that from 14 to get the POH. And we can do the same thing if we have an OH minus and we need to find the pH. With all that, I think we have the basics covered. Thanks for watching, and stay tuned. I might make some more videos about acids and bases. See you in the next video.